Okay, I don't want to take too much time because I know we've got a full presentation today. So I want to thank you all for coming to our inaugural talk for the Climate Resilience Seminar Series. We're really excited to have all of you join today for I think what'll be it's going to be an excellent opening seminar, and it's on flood resilient culvert design. I'm Austin Polobitsky. I'm the incoming chair of the Civil and Environmental Engineering program here at UW-Platteville. And I also serve as the chair of the infrastructure working group that's part of Wiki. This seminar is being offered through a joint effort between Wiki and its home at the Nelson Institute and Platteville. So if just a couple of rules for the seminar today, please remain muted if possible, and feel free to chat questions as they come to you or hold them until the end and use like a raise hand to notify me, and we'll open the floor to you. We've got a full presentation and kind of limited time, so we'd like the presenters to be able to cover everything they set out to, and then we'll get to as many questions as we can at the end. Second, PDHs are going to be issued in about a week following the talk. Now, this is my first time doing this, so you'll have to cut me just a little bit of slack. But essentially what will happen is you need to be on the Zoom call for 45 minutes, and that gets tracked and have registered. And then what'll happen is I'll go through the list and make sure you were on the requisite amount of time, and then I'll issue the live PDH to you by email, the email that you used for registration. Lastly, this seminar is going to be recorded and it's available for later viewing, and I'll send out a link to that location once it's set up, and I've got that finished with our web development team here at Platteville. So without further ado, let me introduce our speakers today. We've got Dale Higgins, who's a retired hydrologist. He's worked for 38 years for the U.S. Forest Service, and with the last 32 years in Chequamegon-Nicolet National Forest. During that time, he worked on over 250 road and stream trail crossing projects. We've got Chris Ester, who's a hydrologist with Chequamegon-Nicolet National Forest, and he conducts hydrologic and geomorphic analysis for flood resilient culvert replacement designs, and also coordinates the culvert program from project identification all the way through to construction. And lastly, but not least, we've got Tyler LeMahieu, who's a civil engineer for the Chequamegon-Nicolet National Forest in northern Wisconsin, and he's the current primary design engineer for flood resilient culverts on the National Forest. And with that, I'm going to mute myself and let these guys.
Okay, thanks, Austin, and thanks to all of you for your interest in this webinar. Our objective today is to give you an overview of the flood resilient culvert design primer and manual that were developed by the Road Stream Crossing Subcommittee of the Wiki Infrastructure Working Group. Okay, so in the webinar today, we'll hope to give you a quick overview of the differences between the primer and the manual, briefly go over traditional culvert design versus flood resilient culvert design and its benefits, and spend the bulk of the time on these 6 design steps. One thing I would like to point out is that this comparison of traditional and flood resilient culvert design is only contained in the primer. Pardon me?
I muted them. Keep going.
Okay. All right. Thanks. So as you might expect, primer is a very concise document, and it essentially tells you what is required and why it might be required, but it doesn't go into the details of how to collect the data or how to perform the analyses. The manual, on the other hand, each section is several pages long, and it goes into much more detail, and not only on what's required, but how to collect the appropriate data or how to perform the required analyses. So next, I'd like to talk a little bit about traditional culvert design, and it's based on a method we refer to as hydrology and hydraulics, or H&H. It's simply just determining the peak discharge and performing a hydraulic analysis, and selecting a culvert size that'll pass the design discharge at an allowable headwater to depth ratio. So what's headwater to depth ratio? Hopefully this diagram will help. Set the stage. Here's the culvert, road prism above it, the water surface, the water flowing from left to right, comes down through here. So the headwater is the depth of water acting on the culvert at the inlet. And then the depth is really just the height of the culvert or the structure. at the inlet. So in this case, the water surface, the headwater depth ratio would be about 0.8. If the water were up where it would overtop the road, it'd be a headwater depth ratio of about 1.9. Okay, so the first step in the traditional H&H is to estimate the design discharge, you need to select a flood frequency. So I need to cover a couple definitions right away. The annual exceedance probability, or AP, you'll hear this a lot today, is the chance a flood will be exceeded in any given year. It's usually expressed as a percentage, but it can be as a fraction. The recurrence interval, or RI, is the average number of years between an event being exceeded. So it's calculated simply by taking the inverse of the AEP fraction. So what that means is that the 1% AEP flood is the same as or equivalent to the 100-year recurrence interval flood. So from a standpoint of design standards, if any are used at all, they tend to vary by agency. You'll see in this table here that commonly the 2 or 4% annual exceedance probability flood is used, which would be equivalent to a 50 or 25-year flood, at a headwater to depth ratio of 1.5 or less in some cases, depending on the site characteristics. So the traditional H&H tends to both minimize culvert size and installation costs. And what that can do is adversely affect both the infrastructure and the ecology. And it does that because it doesn't take into account the geomorphic characteristics or processes of the stream. So then what happens is this results in culverts less than bank full width, high headwater where you get deposition of sediments upstream, high velocity abrasion in the culvert, downstream scour, maintenance problems, increase disruption of aquatic organisms, and these all lead to increased risk of failure. So in the primer, we have 7 key requirements of flood resilient culvert design listed. And throughout the webinar, when you see these, we'll have them highlighted in the same color to help them stand out. I only want to mention a few right now. The first one is that structure width be greater than or equal to bank full width. And the other one is maintaining a minimum hydraulic capacity with the headwater depth ratio less than 0.8 at the 1% annual exceedance probability. Okay, so when it comes to flood resilient culvert design, we've got methods broken out by moderate to high gradient streams and very low gradient streams. So the general concept of this flood resilient culvert design is to design a stream through the crossing and wrap a structure around it. So many of you are probably aware of this classic stream simulation design. And the stream through the crossing is designed based on a nearby reference reach. In our case, we're saying it generally applies to stream gradients greater than about 0.5%. And one key is that you'll always construct a stream bed and a banks through the structure like you see here. Okay, so for very low gradient streams, we're talking about streams that only transport sediment, finer materials, have slopes less than about 0.5%. We have some modifications for Wisconsin. And those modifications are that you set a bank full width culvert at the appropriate elevation. The sides of the culvert act as the banks. Natural sand bed will develop within the culverts. You don't necessarily have to build a bed through, but you can construct rock bars or banks if the depth would be too shallow or the velocity would be too high. So these methods result in greater flood resilience because of greater flood capacity, freeboard at the design discharge, better debris passage, and abrasion protection. So this graph here provides examples of the first two. Here we have a very low gradient stream, bank full width culverts at appropriate elevation. The 1% AEP flood models at this level, so headwater to depth ratio of only 0.53, well within the criteria. And that provides 2.5 feet of freeboard at that design discharge. So I'd also like to point out that the road would not overtop until the flow reaches almost 5 times the 1% AP flood. So greater flood capacity and freeboard. Okay, for consideration of passing wood, study in Northwest California several years ago found that most wood in transport was less than bank full width. And in that case, 99% was. But also that the wood longer than bank full width tended to move parallel to flow. So it turns out these steps are important for promoting wood passage, or these factors. First and foremost, only one opening, avoid this situation, but also no headwater ponding, no constriction. So again, we're talking about bank full width or greater here. Freeboard, and then good alignment at the inlet. So any of those pieces greater than bank full width or moving will pass through. So all conditions that are part of flood resilient culvert design. So another consideration is abrasion. These exposed inverts are subject to abrasion, which dramatically reduces the lifespan of the culvert, and typically failures occur during high flows. With flood resilient culvert design, you have a bed in the structure which protects the invert from abrasion, dramatically increases the lifespan of the culvert. Okay, so the last thing I want to do with this part of the presentation is provide a brief review of a case study of 2016 flood in Northwest Wisconsin. In that case, 8 inches of rain fell in 6 hours, caused catastrophic flooding, caused most stream crossings in the area to fail. During the flood recovery efforts, the Forest Service was able to make a large number of peak flood flow estimates to characterize the extreme nature of the flood. It also happens that they had installed 17 what I will call bank full width culverts in the flood area from 2001 to 2015 prior to the flood. And 16 of those 17 structures survived, even though 13 overtopped. And they survived flows that were anywhere from 2 to almost 7 times the 1% AEP flood. So here are some examples. 3 of these 4 bank full width culverts overtopped somewhat, but they lost no gravel surfacing and required no maintenance. They survived flows that were anywhere from about from more than 1.5 to almost 5 times the 1% flood. A couple more examples here. Not only bank full width culverts, but they had the roads had broad overflow areas, and substantial parts of the flood did go over the road. Lost some minor amounts to more significant amounts of gravel off the road surface, but the road structure survived, only required either a minor or moderate maintenance. These crossings survived flows that were 2.5 to over 4 times the 1% flood. So we're hoping this case study will be published anytime in the next several days. It promotes using flood resilient culvert design as baseline at all crossings, and then considering the vulnerability of the watershed to increase flood flows in the future, also considering the vulnerability of the site to failure at overtopping, and then adding additional design elements as vulnerability increases. With that, I will stop. Thanks.
Okay, so what we're going to do next is walk through each of the 6 chapters and the 2 appendices of the Flood Resilient Culvert Design Manual. And so let me start here with chapter 1, which is all about site assessment. So site assessment is really all about, what essential field data needs to be collected to inform a flood resilient culvert design. And so we're really going to start with what's one of the most important things to identify in the field, and that is characterizing the bank full channel. And as you'll learn today, bank full width is really the most important sizing criteria when it comes to determining structure span. And so what is bank full width? Bank full width is the water surface width measured at the bank full stage. What's bank full stage? Well, bank full stage is the elevation of the water surface at the bank full discharge, also known as the incipient point of flooding. So this is the point where water is about to spill out of its channel and into its floodplain. And the bank full discharge is a frequently occurring peak flow that occurs roughly every 1 to 2 years, depending where you're at. And most of our channels, unless they've been severely impacted, actively feature indicators that are consistent of this bank full stage and bank full width. And so what you want to look for in the field is the first depositional flat that's adjacent to the channel, and the elevation of which should also correspond, if present, to the top of the highest depositional features in the active channel things like the tops of point bars. So moving on to kind of the topographic survey side of field assessment, we need a longitudinal profile survey. So what this is a string of stream thalweg shots to the deepest point of the channel and corresponding water surface shots. And these are taken at every major break and slope of both the water or the thalweg. These need to extend ideally 20 to 30 channel widths upstream and 20 to 30 channel widths downstream. So if we have a 10-foot bankful width channel, we need to be going 200 to 300 feet upstream, 200 to 300 feet downstream. Of course, we need cross sections. At least 4 are needed for hydraulic modeling, 2 upstream and 2 downstream. We need these cross sections to extend through the entire valley, ideally, at least the entire floodplain. And we need them to run perpendicular to flow, both flow in the floodplain and flow in the channel, even if that requires turning those, as you kind of see that non-linear cross section there, which is a common practice. Also, if there's a deep plunge pool below the culvert, with a tailwater control below that pool, we need a cross section right through the high point of that tailwater control. Of course, we need to make sure our survey includes all the necessary topographic shots to characterize the road through the entire floodplain and encompassing any extensive road work. We need to have key shots of structures like low chords of bridges and inverts, bridge decks. Unique to our method, we collect a reference reach. And so what is reference reach? Reference reach is simply a reach of the stream that's outside of the influence of the existing culvert that is close to the same slope as the design reach. And so within our reference reach, we collect additional cross sections, additional bankful width measurements, some detailed sketches of the plan forms and complexity, as well as a pebble count, which we'll kind of talk about a little bit more later. The reason we do this is that the reference reach is used in our method as really the template that we're using to copy the stream characteristics within the culvert. Now, a quick aside, geotechnical information that's gained from either soil borings or drive probing does become really important with larger structures or really any size bottomless structure for forming the foundation design. And as well, we need to assess the risk factors. These can be geomorphic risks, things like head cuts, channel instability, lateral adjustment potential, vertical offsets that are mostly identified in the field. We also need to identify sort of those climate change induced or flooding risks, and those are really 2 parts. So we need to understand and this is done in the office, the characteristics of the watershed that would lead it to be vulnerable or resilient to flood flows increasing at the site. And also we need to understand, so that's the watershed scale. At the site scale, we need to look for factors such as lack of a floodplain, steep stream channels, or poor alignment that would cause it to be a riskier site. Chapter 2.
Okay, I'll go ahead and cover Chapter 2 hydrology from the manual. And here we go. The chapter covers what flows are needed and how they can be determined, and a few other topics, and that's what I'll touch on today. We have 4 methods for determining flood flows, but I'll focus primarily on the first one, stream stats. So what flows are needed? Well, an absolute minimum, I've already mentioned the 1% AEP or the 100-year recurrence interval flood is needed, so you can check that headwater to depth ratio and make sure it's less than 0.8. If you have a moderate to high gradient site and you're going to need to do a sediment mobility stability analysis, you need a wide range of peak flows for that. And then we also encourage you to determine that 1.5-year recurrence interval flood, which associates with bankful, and that can help you with your analysis. So I'll start with that first flood flow method, which we list as stream stats and the Wisconsin regression equations. I personally consider them in most cases to be the most accurate method and most commonly used too in Wisconsin. Accuracy because they're based on observed flood flows at gauging stations. The regression equations use watershed and climatic variables to estimate the flood flows, and you have separate equations for different regions of the state. They're also easy to use, and that's because U.S. Geological Survey has developed an online tool called Stream Stats, and that tool will delineate the watershed for you, determine the basin characteristics, and solve the equations. So this document on the left describes the most recent version of the regression equations, flood flow regression equations for Wisconsin, which were developed in 2022. The map on the right shows the 4 current flood frequency regions in the state, and the little dots scattered around are the locations of all the stream gauges that were used to develop the equations. So this table here gives an example of the regression equations, and in this case, for one of the regions, there are 8 different AEPs that are estimated from the 50% or 2-year flood all the way down to the 0.2% AEP or 500-year flood. So pretty wide range of flood flows provided. Here's an example of the watershed delineation by done in stream stats. And the key here is you always need to review this to make sure that's accurate before you forge ahead with your analysis. There's an example of the output from stream stats. The upper area are the input parameters that were determined by stream stats to run the regression equations. The lower part are the results with the flood flow estimates here for those 8 different AEP floods. And it also includes upper and lower prediction limits for the flood flow estimates and standard error of estimate in percent for the estimate. So one flood flow the regression equations do not provide is the 1.5-year flood, which associates with bank full flows. So an easy way to do that, though, is just plot the points, extend the line down to obtain that value. Okay, next method in the chapter is goes over the transfer flood flows from a nearby gauge for your AP of interest. We suggest you consider that either as a second method or if you have some concerns about the accuracy of the regression equations. So here's an example of the equation and how to determine that exponent for the equation. So the third method is this what I call rather novel approach called the flood potential portal, which predicts large magnitude and stream floods. So an online map-based system, and it'll provide estimates of an expected flood potential and a maximum likely flood potential. It will, for ungauged sites, and it will also solve the US regression equation, so it's handy from that standpoint. Last item in the chapter, which gets the least attention, are rainfall runoff models, but it does touch on them briefly and go over the advantages and disadvantages of that method. A couple other items in the chapter. There's a short section on future conditions, hydrology. All I'll say today is that it points out that not only will future floods be affected by climate change, but also by watershed characteristics, and how do you take that into account for these long-lasting structures. And then finally, the chapter's got some suggestions for how to estimate bypass flows if you choose to do so. So with that, I'll pass it on to Tyler, I believe, or Chris. Chris.
Yep, me again. So chapter 3 of the manual covers alignment and profile. And these are lumped together because they're often done concurrently and iteratively, but they are separate steps, and typically alignment is looked at first. And so when it comes to alignment, there's really one key core principle. We must align the inlet of the structure with the upstream channel. And this is really essential for passing flood debris. Where our stream and our road don't meet at a 90-degree angle, which happens all the time, there's really 3 options for achieving good alignment. And the first one is shown here, which is the most frequent, most common. We can lengthen the culvert and skew it to better align the inlet with the channel upstream. Downstream alignment doesn't matter as much. A second option for achieving good alignment is we can actually keep the culvert in its existing location, but we can realign the channel. Now, a couple caveats with this. We must make sure that we're not over steepening our channel if we're not accounting for it by shortening the length. And we also, of course, need to, this includes, some excavation in wetlands and stream channels. So we must make sure that DNR is on board with our proposal. A third option is we could actually move the culvert and then dig a new channel downstream. And so this is something that we've liked to do recently. We're actually able to go with a shorter, less skewed culvert simply because we're putting the culvert right where the stream first hits the road, and then digging a new downstream channel. Again, pending approval from DNR for that dredging. So once we've determined our alignment, we then move on to our profile. And this is our longitudinal profile data that's been plotted. And a profile analysis really seeks to provide what's called a design profile that maintains the natural elevation and slope of the stream by setting a bankful width culvert at the right slope and elevation, embedding that bankful width culvert at least a foot into the stream bed based on the design profile. So the first step after our longitudinal profile is plotted is to determine the existing profile slope. And so for linear profiles like both of these, that can often be done simply by looking at the trend line of the thalweg and the water surface data. So in the case of the above profile, that's low gradient, you can see we have a slope of 0.12%. So that clearly falls within our very low gradient method. And in the case of the lower profile, which is at 1.2%, that needs to fall within our moderate to high gradient method. And so this is that really key first step that determines which of the two design methods we're going to follow for the rest of the design. So if we have a linear, non-impacted, low gradient stream profile, such as this one right here, our analysis really of the profile to determine our invert elevation is pretty simple. It's 4 basic steps. So we're going to connect our high points of our profile or our grade controls. And we're going to look at then how deep the pools are scouring. And typically the design profile then is where we're going to expect the average thalweg elevation to set up through our crossing, so somewhere right in between. And then our method dictates that we need to embed that bankful width culvert at least 1 foot below the design profile. And that's going to allow that 1 to 2 foot of embedment of natural material to be deposited and maintained within the structure. Couple of things. Typically with low gradient designs, we are setting culverts flat, but you don't have to if there's a slight slope or it's a longer culvert. And we're also typically using full invert structures because it simply just helps with the scour protection issue. We rarely use bottomless structures with our low gradient design. And 1 foot of embedment would be a bare minimum and typically applicable to small streams, but we're very, very frequently going to 2 feet or more of embedment on larger streams or deep streams that scour deeper pools. And certainly additional scour analysis on any sort of bottomless structure might tend to put the bottom of your footings or your invert even lower than this. But we're saying 1 foot of embedment would be the bare minimum. But low gradient profiles are sometimes not linear like that last one because they're very susceptible to impacts. And those impacts are typically obvious by upstream ponding, so a raising of the water surface elevation upstream, and upstream aggradation, so excess deposition of sediments upstream. And so the designer needs to be aware of the causes and the effects of impacts to profiles when we're doing this analysis. So I'm going to just give you the 2 most common impacts. One, and by far the most common, is a set high existing culvert. This red line is the invert of the existing culvert, which is easily 2 feet above the downstream channel. And you can see it's evidenced by ponding and aggradation. And so in these cases, we must make sure that we base our design profile only on the downstream channel and extend that up through upstream at the same slope, and expecting that the upstream channel will eventually downcut and restore itself to its original elevation. Setting our culvert then at least 1 foot below that design profile. Another very common impactor to profiles in low gradient streams is to have a slug of sediment sitting downstream from a history of past washouts. And these need to be accounted for by determining our design profile based on our furthest downstream reach. Sometimes you can get lucky and it can connect further upstream as well. That's going to be way below the elevation of that slug of sediment. And so we need to make sure that we're not only putting a culvert at least a foot below that design profile, but we're also in our plans excavating down to our design profile and removing that excessive deposit of material for a couple of reasons. Number one, it's going to restore the stream ecology and temperature upstream, going to be a great restoration of the stream. But more importantly, I would say, without doing that, that slug of sediment will act as a dam, continuing to elevate the elevation of the stage of flood flows through our crossings. That's a key element of achieving flood resilience. So that's some key things with low gradient profiles. Moving on to high gradient profiles now, following our moderate to high gradient method. There's much more involved with this because we're using this to determine the part of the design of our channel through a structure. So the manual presents 12 steps for analyzing the longitudinal profile and 8 steps for the development of the design profile in moderate to high gradient sites. So a couple of key differences. Rather than a single slope line, like I showed you with the low gradient sites, there's going to be many slope segments that are delineated. And the stability level of grade controls are going to be ranked. And so our design profile in high gradient streams is determined by stretching a line between the most stable grade controls directly downstream of the crossing with the most stable grade controls directly upstream of the crossing and tying into those. We then look for a segment of the stream that is most closely matching the slope of this design profile as our reference reach, and one that, again, is outside the influence of the crossing. And we're also using this design profile to base the elevation, slope, and sequence of our constructed bed forms, or our riffles and pools within our constructed channel. Another key difference and a source of a lot of the other steps is we create something called the lower vertical adjustment potential, and that in this example is the yellow line. So this is a geomorphic scour analysis, and it's done by multiplying our residual pool depths by an adjustment factor. And so when it comes to setting the culvert, invert, and slope at a moderate to high gradient site, in addition to setting it at the grade and below our design profile, we also are needing to set the bottom of the footer or the invert below our lower vertical adjustment potential. There's much more in the manual in chapter 3, but those are the high points, and I'll leave it there and pass it to Tyler.
Yeah, hello, it's Tyler now speaking to you, and we're gonna start with walking through what's in chapter 4 of the manual, bed and bank design. So we'll talk through why do we design a bed and banks, and then we'll get into some how-to for these higher gradient sites versus lower gradient sites. So why are we putting a bed and banks in our pipe? Well, remember, our streams are moving more than just water, right? They're moving wood and debris, right? Ideally, they're moving fish, other organisms, and certainly they're moving bed material. And bed material is kind of the point of question as we think about installing a bed, right? You can see all those things present essentially in the pictures to the right. And anywhere where there's a lack of continuity in some process, water, debris, bed material, that's a failure point or a point of tension. And we can make our structures perform better by providing that continuity. Secondly, these are generally going to be upgrades to infrastructure, right? They're going to be a little bit bigger pipe or a lot bit bigger pipe. And if that infrastructure investment is going to be worth it, it needs to last a long time. And embedment is one way that we can help achieve that. If there's a stream bed in a pipe, it's going to protect that pipe against abrasion that might shorten that pipe's life. Here's a couple pictures of whole trees moving through these flood resilient structures. So they really do work. And after we've looked at our reference reach, we should know if our site is on the higher gradient end of the line or the lower gradient side. And the road we take for designing bed and banks looks a little different depending on which we're in. So for these higher gradient sites, we're going to design a bed that mobilizes at the same flood flows as the natural channel, confined within stable banks. Why do we need banks? Well, these are higher energy systems that have more stream power, and they will happily find that nice, smooth culvert sidewall and dig there to their heart's content if you let them. Right? So what's different about low gradient sites is our water's moving slower, right? It's usually backwatered, there's less stream energy, it's not going to dig in the same way. So we can generally just get away with a pipe that is bank full width. And there's some other simplifications that we'll get to in a minute. But let's start with higher gradient sites. How are we designing our bed and banks? Well, first, vertically, what are we putting there? Well, we're looking at that reference reach long profile, right? And whatever that sequence is, if it's a riffle pool sequence, maybe there's some steps, whatever it is, we're going to copy that and paste it essentially through our reference reach, or excuse me, through our pipe, tying that into grade controls up and downstream. Horizontally, so in cross section, every one of those relevant features, whether it's a riffle or a step, we will have surveyed a cross section in the reference reach. And from that cross section, we can create a easily constructible approximation that will be specified within our pipe. And again, high gradient site, right? So that's going to include both the stream bed and banks. Here's what that might look like. Right there is our surveyed cross section. We start to play with that and create a approximated version that's a little more easily constructible. Then maybe we start to break that into bed and bank components and play with structures. And then we land at something that is easily constructible, it makes sense, and it works at our site. In 3D, it might look something like this, right? The nice pink culvert with head walls, wing walls, and brown banks and a blue bed. Okay. But what are we going to put in our pipe? Well, let's start with the stream bed. Remember, our goal is that our stream bed mobilize at the same flood flows as the natural stream bed. And to figure out what gradation we need to accomplish that, we'll do a pebble count. And that's simply walking transects, grabbing random particles and measuring the intermediate axis to get a particle size distribution. It's usually measuring an armored layer, so we might have to supplement some fines so that our flow doesn't go subsurface. And then to specify what we put into the pipe, we take that particle size distribution from the reference reach and we'll break it into components which are easily comprised of readily available material. So maybe we have, maybe we use some 3/4 inch road gravel, and then we mix it with some 4-inch crushed stone, whatever is available. And you'll then specify readily mixable ratios of those various things to create your mix that approximates what you measured. Right? Still in our stream bed, there might be key pieces, right? These are large particles, they don't move. They do serve a purpose in maintaining some of that channel form. And generally, we're going to specify these separately. So they might be specified individually, like you see on the right there, or they might be specified just by saying, use some of your bank mix and put it here, here, and here. Now, how do we get our bank mix? Well, remember, our goal is stable, immobile banks that confine our bed. And natural banks do this really well. Usually there's some component of roots and wood in them, but it's hard to grow plants within a pipe. So we use big rocks. And to figure out how big our rocks need to be, we're going to do a stability analysis. That will get discussed a little later. And again, key here is to start with that, whatever that large stable particle needs to be. We'll start there and then again specify simple, easily available materials to fill out a mix that then fills those voids. Because again, we don't want water to go subsurface through voids. Let's shift over to low gradient sites. Vertically, what are we doing? Well, there's not actually much happening vertically usually through these sites, so we can usually just set a pipe flat. Now, as pipes start getting longer, it can still be better to start sloping a pipe, but often set flat works great. And horizontally, we've touched on it already, but usually we're just going to specify a pipe that is at bank full width, no wider. Because it turns out these pipe sidewalls tend to really effectively simulate vertical banks in a lot of these low gradient systems. Picture like a sedge meadow with nice stable vertical banks. What are we doing for a stream bed? Well, usually not much. Often in these systems, there's a lot of material being mobilized pretty consistently, especially in sand beds. And if we set a pipe sufficiently low, there's generally enough material present upstream that it will naturally self-embed after installation. Now, maybe there's a ton of material that you need to fill in that pipe and you're not sure in that system that it's going to be present upstream. Maybe you're worried about a head cut. Those might be scenarios when you do install a stream bed up front. And what do we do for banks? Well, we already touched on it, right? In low gradient systems, the culvert sidewall really works as the banks. Certainly you can specify a wider structure and put banks in. You might do that if you're trying to also accommodate terrestrial organisms, but again, generally there's no need. In these low gradient systems, it often looks like this. It's a bankful width structure. It's set flat, a foot, 2 feet below the thalweg, and it's allowed to just naturally embed, fill in naturally. Now, little caveat, if thinking about aquatic organism passage through the whole range of flows a site might see, during low flow, there may be sites where you get too shallow of a channel. So you might consider adding some structure like rock bars or something to simulate what's in the natural channel and maintain a deeper channel for fish during low flow conditions. All right, let's pivot to chapter 5 of the manual, which contains structure selection and design. So as we run through this, we'll talk about overall, what's our goal? What are we doing? We'll talk about how we size our pipe in the flood resilient method. We'll go over some common structures that might apply, and then we might look at some differences in high and low gradient sites. Our structure is really where all the different things we are discussing today come together, right? We got to accommodate all these other design considerations. And not only that, but we need to meet all the road and traffic considerations, every other bit of site need needs to all come together at our structure. And traditionally, with hydraulic design, right, we have a design flow, and we're going to size a pipe to cost efficiently pass that flow. We can kind of get to a right answer, and it feels good to us engineers, right? The flood resilient method is somewhat different, right? We're starting with a design stream and then wrapping a structure around it. And there's often more than one way to achieve that goal. The figure on the right demonstrates that with 5 accommodating the same stream. And it's really no less of a design problem. One key component to designing flood resilient structures is a long life. Like we mentioned, these are infrastructure upgrades. And if that upgrade is going to be worth it, it needs to be there for a long time, right? So how do we size our pipe? Flood resilient method? Well, we start with bankful, right? If it's a low gradient site, we're just going to start with a pipe that's bankful width. If it's a high gradient site, we're going to fit bed and banks. Then we're going to look vertically. On the lower side, right, our goal is to have our pipe consistently embedded through its whole life. So we're going to look at the lower vertical adjustment potential and make sure our invert or our foundations are set below that. So you might run scour analysis, especially for bottomless structures. And then if we look up, right, where's our road? Do we have very little fill to work with? Do we have a lot of fill to work with? Can we raise our road? Can we not? These 3 factors start to really narrow down one by one what commercially available structures are available to us, right? And then we settle on something. And finally, we check the hydraulics. And usually we come out right around our design objective, or it overachieves to some degree. And certainly this process is iterative. So what might we use? Well, the common ones would be a corrugated metal pipe, right? A round pipe. It's probably familiar to many of you. And then we have pipe arches, very similar. It's just a squashed round. And we start to get a wider structure for a given rise with the pipe arch. Once we're dealing with bigger structures that we can't build with a single piece, we'll start looking at various structural plate structures. Aluminum boxes are one of them. They come in a lot of sizes, right? And they're great for a lot of these Midwest sites because that have low fill. They can accommodate a quite wide span for a given rise, right? And then concrete boxes. They're very flexible, right, on the span and rise combinations with the depth of cover requirements over them. So they're kind of in a class of their own. Materials, right? We have concrete. Concrete's strong, it's durable, it's long lasting, it's heavy, it resists buoyancy. It's kind of the Cadillac if you can afford it for these applications. It can come at a little greater cost. But steel is probably what we see most commonly installed, right? It comes in a number of coatings. Galvanized usually isn't going to be long enough lasting to be the best fit for these applications, where aluminized or poly-coated pipes will serve better. In particular, we use a lot of polymer-coated pipes. We expect 75, 100 or more years out of them. Aluminum is another material available, right? It's lightweight, which is helpful for larger structures, and it is very long-lasting as well. So serves its purpose well. And as a note, plastic pipes, for a number of reasons, don't really work well for these flood resilient crossings, so we'd recommend not using them. End treatments, ton more here in the manual. I'll just briefly speak to step bevels. It's a low-cost end treatment that gives you notably improved inlet hydraulics and improves your flood passage, especially when debris starts to accumulate. So fits a lot of structures well, especially ones with full inverts. But look to the manual for more. And lastly, the site gradient and its impact on our structure selection. Most notably, you're just considering what needs to be built in the pipe. So if you've got a bed and banks to build, you need to make sure you can do that, whether that be with a stem wall that you construct the bed and banks before the top of the pipe, or providing enough headroom. So with that, we'll jump to the next section, but I just want to highlight there's a lot more to this one in the manual. In particular, foundation design can become pretty important as we start to look at bigger structures. So look there for more.
Okay, thanks, Tyler. I'll be covering this next section, which is Chapter 6, Hydraulic Analysis. Okay, in the manual, we have 6 analyses listed that you can perform. The 3 here are highlighted, are part of those key requirements we talked about. And I'll touch on each one of these very briefly. But before I get started, just want to cover a few background items. The examples you'll see here of hydraulic analysis were performed with HECRAS, which is publicly available to everyone. It's a very functional program. There's another publicly available program, hydraulic model, HY8, which is easy to use, not quite as robust as HECRAS. And then we also have a few what I might call tips or suggestions for you if you're doing hydraulic modeling. One would be always model the existing structure. It'll help you decipher the current condition, history of that structure, will help you with determining model accuracy. Does it match, the reported history? We have also mentioned that modeling that 1.5-year flood as it relates to bank full can help verify your flood flows and accuracy of the model. A couple other items: if you have a moderate to high gradient site, you're going to do sediment mobility, stability analyses. You need to use the lid option to be able to get those hydraulic parameters from inside your structure. And then for very low gradient sites, you can use the depth block option in Culvert editor to mimic the stream bed. So one last item, if you're interested in using HECRAS, you have limited experience, we've got some of the basics laid out in the manual in Appendix C. So I'll start with that. First, hydraulic analysis, the most important one, verify that the headwater depth ratio is less than 0.8 at the 1% AEP flood. So here's an example, very low gradient stream, bank full width culvert. And what you see here is the hydraulic modeling. Both the headwater and the depth were determined from the top of the assumed top of the bed in the culvert. And so in this case, easily met that criteria with a headwater depth ratio of 0.54. Okay, another value of setting up hydraulic modeling and doing modeling is you can use results and different types of results for all kinds of uses in terms of permitting or environmental effects. Here's just one very simple example. You can show the change in the headwater depth ratio from the existing to proposed here, or you can actually look at the absolute value. So in this case, the headwater at the 1% AP flood was going to decrease almost 3 3/4 feet. So again, important for the moderate to high gradient sites, you need to do a stream bed mobility and stability analyses. The hydraulic calculations come from a program like HECRAS, and the idea is you want to make sure that the bed mobilizes in your constructed reach in the culvert at the same flow as within the reference reach. And so this final analyses can be conducted in a spreadsheet. So here's an example. You can cut and paste data out of HECRAS into these yellow columns. There's 3 groups of rows here. The first set are for the reference reach, then preliminary stream simulation design, adjusted design. And so you use shear stress calculations. You enter the D50, D84 over on the right side. And then in this particular case, the reference, the bed mobilized at a lower discharge. So then the bed material is increased by 10% to get equal mobility. And when it comes to stream beds, key piece stability, it's the same sort of process, only you're using the key pieces, and then you're looking for stability across your range of flows, and you can verify that. And then the next thing, if you have a model set up, you can use it to evaluate the resiliency to extreme flood. So here's a case where you can model the flow that will just overtop the road. And in this case, it was exactly 2 times the 1% AEP flood. And you also see there's a low point off to the side of the structure. So the flood could get a half a foot deep over the road and not really impinge on the structure yet. So at this point, a designer could consider, well, what's the vulnerability of the watershed? How likely is this to happen? If it happened, would the road survive? Do I need additional features? So you get a sense of the type of analysis you can do very quickly with regard to evaluating extreme floods. And then the last item I want to touch on is in Wisconsin, for structures greater than or equal to 20 feet with an open bottom, you need to conduct a Federal Highway Administration scour analysis. There's some references here on how to do it. It's detailed enough. You probably need a civil engineer to do it, or maybe a hydrologist. One thing I do want to point out is that it's different from that geomorphic scour analysis and lower vertical adjustment potential. It's a different type of analysis. And again, I'd reiterate, if you're on a low gradient sand bed system, go ahead and use an invert, and that'll protect you from worrying about scour analysis. Okay, so that ends that portion. The next thing I want to do is just very quickly go over an example of a design for a high gradient stream. And I just point out that the construction design plans for this particular site are in Appendix A of the manual. Okay, so what I plan to do is go over these 6 design steps very quickly. First, I'd like to, on this aerial photo, show you the road, the site. The high gradient stream section is right in here, but there's also a very low gradient segment just above that. Okay, site assessment standpoint, Fisk Passage was a major concern, structure condition. There also is significant blowdown just upstream of the culvert and the steep channel. Survey standpoint, survey of the stream profile here. Cross sections, as Chris described, started out with 7, and then once the reference reach was identified, 4 more were added. There were some more detailed survey of the bed and banks in the vicinity of the culvert, and then lots of road points as well. So once the reference reach was identified, pebble count was conducted there. Key pieces are also measured throughout the entire surveyed reach. And one thing you'll see, these are numbers in millimeters, but they're large particle sizes. I think it's the largest bed I think I ever worked on, and you can see that easily in some of the photographs too. So from a hydrology standpoint, at the time of the analysis, Stream Stats had just implemented the watershed characteristics portion. So that was used to delineate the watershed and determine those characteristics. But then the 2003 Wisconsin regression equations were solved in a spreadsheet to come up with the flood flows. Okay, in this particular case, the alignment was good, especially at the inlet, so there's no change needed there. So the profile is plotted and analyzed to identify that design profile and reference reach and develop that lower vertical adjustment potential, or LVAP. So the profile was broken up into 5 segments like Chris described, with great controls at the ends of each one. Interesting enough, they varied from 1.9% as the gradient was flattening out above the culvert to, we had a short stretch that was 12%. The design profile, which ran from these 2 grade controls, was 2.9%. And then the reference reach that was identified was 3.0%. Now, the LVAP, which flows through here, is almost 4 feet below the existing culvert. So any invert of a new structure or footer would have to be down below that line. So the typical cross-section from the reference reach was used to develop a typical cross-section for the bed construction of culvert with 2-foot banks added on each side, bed mix determined, like Tyler mentioned, from a particle size distribution. Those two were mated together, and it was determined that this design bed would fit within a very large pipe arch culvert and be able to fit below that lower vertical adjustment potential. So this slide here just shows the site sketch from the reference reach and photograph from the reference reach and how they were used to help design the bed through the crossing. And here's a plan view of that in the construction plans and the specification of stream bed mix here. These are also from the construction plans, shows both the culvert and the bed in cross section and profile view. And then from a hydraulic standpoint, you know, two big steps: verify the headwater to depth ratio. That was met very easily with a headwater to depth ratio of 0.39. And then in this particular case, you know, normally you want to have the beds mobilize in the structure and reference reach at the same time. But, you know, all you have to do is look at this channel, extremely coarse, steep channel. And we anticipated it to be extremely stable, and especially given that low gradient segment upstream, that was unlikely to deliver any kind of material this size. So we anticipated that the bed would be very stable. And the analysis confirmed that's the beauty of the reference reach, I think. So here's a HECRAS plan view, the culvert with the lid on it, and the reference reach, and the 2 cross sections. Here's with the one in the culvert and the one in the reference reach that provide the hydraulic data, and then the analysis in the spreadsheet, which confirmed that they were beds were stable across the entire range of flows looked at. So with that, this was the end result. So I'll pass it to Chris.
So Appendix B of the manual has the plan set for a very low gradient design. And, you know, I really don't have time to go much through this. I'll just say really fast, there was no risk factors. The flood flows were low. The alignment was good. Gradient was low. Set the culvert about 1.5 feet below the design profile. Chose a pipe arch that was right at bank full width, embedded there to naturally fill with sand. Used our typical poly-coated steel pipe arch for long life, bevel cut ends. Headwater to depth ratio met our standard. Worked with Coleman Engineering up in the UP, who did a great job with the plan set, and ultimately came out with a great solution. So I think the take home is, you know, flood resilient culvert design does not have to be complicated. And I would say for us, 90% of what we do are low gradient streams in northern Wisconsin. And this culvert is still working on embedding. This is taken right after construction. It can take up to a couple years for that culvert to embed. So here's our email addresses, and that really concludes the presentation. Please feel free to reach out to us with additional questions. These resources are on Wiki's website now, publicly available. Please let us know if you see any. Please share those widely and let us know. We're happy to work on edition 2 if there's little tweaks that need to be made. And I think with our last 30 seconds, we will answer a few questions. But I did want to say, Dale, Tyler, and I, and Austin are happy to stay on after 4 o'clock if anyone is able to, and has some burning questions for us, because I see we are out of time. So I appreciate everyone who was able to block this out. And I guess at this point, Austin, is there any questions we could answer off the bat?
Yep, I've got a couple, but I think right before we do that, I'm going to steal your screen share from you, if you don't mind. Stop sharing for just one second.
Yeah.
Okay, so I just want to show you all 2 things, and then we're going to do questions. If you go to the Infrastructure Working Group webpage at Wiki, and you can just Google Wiki Infrastructure Working Group, to get to where the documents are, all you have to do from that front landing page is click on Initiatives. And here's different initiatives and data, you know, whether it's Wisconsin Rainfall Project or other surveys, other things that we've done. Down at the bottom here, we've got the flood resilient road stream crossings, and both the primer and the manual are there, and you should be able to click on them and download them as PDFs. Last thing before we get to questions, at Platteville, we have a website, a landing page for the Climate Resiliency Seminar Series. The recording, once we download it, we'll go post it up here. All future seminar events will also be on this website, and you'll go through the same process to register for those talks in the future. And eventually, if you give me a little bit of time, I will send out a link where you'll be able to request the PDH also through this website. So I'm going to stop sharing. I'll let Tyler and Chris share their screen. One of the first questions, and I think it's a good one because you guys actually answered this for me yesterday. Why not use bottomless culverts for low gradient streams? I think that's a great question.
Yeah, I can take it. And I guess to be upfront, we're not saying don't use bottomless structures, right? It's actually more of a practicality thing. It doesn't end up typically being a cost-effective solution, and it's more involved, right? If you're putting in a bottomless structure, you need a footing of some sort, right? And certainly you can do that, but then you need to be doing a different level of scour analysis. It's a little bit different approach, right, you're generally going to be digging deeper. You're going to be improving the foundations. So it doesn't generally end up being cost effective over a full invert structure for kind of your cookie cutter low gradient system where you could just throw in a pipe arch, right? Now, there's certainly applications where it makes a lot more sense, right? A good example would be on a higher gradient system where you are installing a full bed and banks, and it serves you well to not have to put in a full invert before you go place that material, and then you can cap the material only after it's placing something on those footings. So I hope that answers the question. All right.
And it looks like a second question was, are you suggesting whether a culvert is 2 foot in diameter or 84-inch diameter, you should still bury at a minimum of 1 foot?
Yeah, that is a fantastic question. The guidance is generally that we need at least a foot of embedment, but this method is really for streams. And so it's very rare that we're installing a stream culvert less than 3 feet. I've never worked on one around 2 feet or a 24-inch culvert, because again, we're putting in bankful width culverts. Typically anything under 3 feet is probably not going to be a stream, but I've worked on several 3-foot streams, and this is a great point. No, I'm not embedding it 1 foot in it if I'm using a 3-foot culvert. Typically doing something more appropriate, like 6 to 8 inches of embedment on a 3-foot culvert. But I would say starting at a 4-foot culvert and on up, 1 foot of embedment is very appropriate. But to your point, on the high end of that, often 1 foot of embedment is not enough when we're getting in any structure, let's say over 8 or 10 feet. Wanting to embed that closer to 2 feet. But just for simplicity, we say in most cases you're going to want to achieve at least 1 foot of embedment.
And I'd add just some of that might be related to like your determination of the lower vertical adjustment, right? Like the smaller streams tend to have a lower, I guess, variability in the depth of their pools, and the gradient plays into that, right? But once you get bigger streams, that a 2-foot pool is more common in a bigger stream than in a little stream. So right, having more embedment in those systems where the bed changes more is relevant.
2 more questions for you guys. First, are you having to conduct flood map revisions? And then the second question is, have you incorporated flood relief culverts or road dips at any of your sites?
And Dale, do you want to take this? And did you have a go back on the last question?
Sure. I'll start on that. In terms of flood relief culverts, my general advice would be, especially on these low grading streams of broad flood prone areas, but if you need the extra capacity, put it into the main structure first for debris passage and that sort of thing. I would look more to put in flood relief culverts, say where you have upland floodplains or you see flood swales and that sort of thing, then I would definitely look to that. Now, in terms of overflow areas, I wouldn't, promote overflow areas at lower flood flows, but if you meet all these design criteria, I would definitely encourage overflow areas if you have the room. So in a lot of cases, I know in the forest, we put in larger pipes in those broad flood prone areas. And by putting in much larger pipes, we had to like ramp up and over it, and it would leave low areas on one or both sides of the structure. And a lot of times that's where, when you get an extreme flood, that's where it'll overtop and the road can still survive. That certainly was the case with some of the, the case history from the Northwest 2016 flood. So if you have the room to do that, absolutely yes. Yeah, they can really enhance survivability.
And then the question about flood map revisions. Are we doing those through our designs? And I would say, we're working with our county zoning staff, typically providing them our headcrest analysis, and that's usually as far as it goes for the floodplains that we typically work in.
Other questions, feel free to chat or, oh, looks like another one just came in. Are you guys able to see that one, or do you want me to?
We can see it.
Okay, I'll let you take it.
We put in a culvert for a project and the culvert completely froze solid when we had a melting event. The water overtopped the gravel road and washed out some of it. How can we prevent the culvert from freezing?
Well, I'll start here, and then maybe you guys can help me out. But I'm looking at the photo. I assume that's the picture there, and so I see a couple things. One, I see two structures rather than one, and they look like they're up awfully high. So the first thing I would say is, this flood resilient culvert design, the culvert would be bigger and set lower, so that may buy you quite a bit. But without knowing all the details, what type of stream it is and that sort of things, it's hard to go much beyond that. I have seen a few cases where there is tremendous ice buildup in the culvert, but it never completely filled the culvert, and the base flow kept flowing underneath the ice in the culvert in a few cases. So I don't know if either of you have any more comments about that.
No, I think that's exactly what I would say. A bank full, I've never seen a bank full with culvert so full of ice that it couldn't have additional capacity. So I think what you're dealing with is just those culverts aren't big enough or set low enough. Because typically base flows occur in the winter, so ice is generally going to be at bank full level or lower, which, what we're proposing, our culverts are going to be extending much above that level for extra freeboard if they do freeze.
Okay, well, I'm gonna stop the recording. People are welcome to stay on. I think Chris, Tyler, and Dale, you probably have 5 or 10 more minutes, maybe, if there's some other questions, if people want to unmute or video. But that concludes our inaugural seminar. Thank you, Dale. Thank you, Chris. Thank you, Tyler. I really appreciate it. It's excellent talk. We're really excited to get this manual out to everyone in the state. And again, use the links I posted in chat, or feel free to navigate to our Wiki Infrastructure Working Group page.